Hey guys, welcome back. Today I want to ask and answer a very simple question, and that's how much collet could a collet chuck if a collet chuck could chuck collets? No, wait a second, that's a different video. What I actually need is a collet chuck for the lathe. I currently have a few handles which I need to hold so I can face off the end and then polish it up. And I'll probably use a form tool to round off the corners at the same time. Now as you can probably see, I've already sanded up one end, and I don't want the chuck jaws to bite in or scuff up the end and ruin the finish. Now normally my go-to in order to avoid this would just be to use these copper soft jaws which I made from some copper pipe. They simply just sit on the top and they prevent the teeth from biting in. Now on the whole they do seem to work quite well, but they also reduce the amount of grip or bite that the jaws can put onto a part, and under heavier loads I have had parts slip and ultimately scuff up in the chuck. Again, that's usually under heavier loads, but I will be coming in with a form tool and rounding off the end, and that won't be a light cut. Couple that with the fact that the run out in the chuck is a little bit worse when I'm using these soft jaws, I'm usually inclined to find some sort of alternative when run out is important. Now obviously I could go with the 4-jaw, the holding power is usually a lot better with the extra jaw, and once it's dialed in, the run out is almost non-existent. But I do have quite a lot of these to polish up, and I don't want to spend hours here dialing parts in. The parts aren't all the same size, so I will be spending a bit of time trying to dial out that run out. I know some people are very quick at doing this, but me, not so much. Which brings me back to the collet chuck, or in this case, it's more so a collet holder. You've seen me use this one hundreds of times before. It takes an ER32 collet, it has a morse taper on the end, which allows me to use it either in the mill or the lathe, either for holding end mills or parts. And to stop the taper from coming unstuck when I'm using it, I also have a drawbar for the lathe. It screws into the back and it pretty much holds it in place. And for what it's worth, whilst I really like collets, ER collets are my go-to. For one, I've already bought the expensive set, so I'm inclined to use it, but outside of that, I really do like them. They have a pretty good clamping range of about 1mm or so. So this one here is 18mm, but it should be able to shrink down and hold anything to within about 17mm. I know it probably doesn't sound like a lot, but this morse taper collet which I have here struggles to hold anything about 20 microns smaller than what it's really meant to hold onto. And as a result, I don't need to keep a huge set of collets on hand. I think this should do anywhere from 3 up to about 20mm. And obviously it has a massive clamping area, so it's able to grip onto parts really well without scuffing them up. Which is really going to be my biggest benefit when I'm turning down these handles. And obviously it being a collet, the run out should be less than 10 microns, which for most applications is more than enough. So at this point you're probably wondering why I'm making this video, given I've already shown you my current collet chuck, which I've already used in previous projects. Well, good question. The collet chuck that I have here is really only meant to be used with end mills. Obviously you can use it to hold parts, but unless your part is 10 to 12mm or smaller, you only have about 35mm of length to push up into the collet chuck to be able to hold it. Which for small parts is fine, but for this project it is not going to be enough. So my plan for this project is to make a proper collet chuck for the lathe that'll sit onto the spindle nose and bolt into place, rather than fitting into the lathe taper and relying on some sort of drawbar to hold it in place. Doing it this way should be a lot more rigid and it should produce a much better chuck. Technically, I have done this project once before, but that was for the much smaller lathe, and that chuck, it's really undersized even if I made an adapter for this lathe. I have a piece of 1045 medium tensile steel. It's roughly 130mm in diameter and about 60mm long, and it was about $60 to buy. That's roughly half to a quarter of the price of a pre-made one. Now the last time I did this, I think I used low carbon 1020 steel, and that held up just fine, so 1045 is going to be more than enough. So let's get it loaded up in the lathe and let's start machining. So the first thing I'm going to do is I'm going to face off what's going to become the back face of the chuck. I'll start off with these CCMT inserts. They seem to work the best for these large facing operations. Now that cleaned up quite nicely, although the surface finish is a little bit worse than what I was hoping for. So I'll do a lighter cut with a finishing insert and hopefully that should clean it up. And that is looking a lot better than it was looking before. What I need to do now is cut the register that will interface with the flange on the spindle nodes. It's basically just a counterboard recess, which shouldn't be too difficult, except needs to be spot on. I mean exactly spot on size, which in this case is 95mm exactly. Any larger and the chuck won't locate perfectly concentrically, and it will throw all the work off centerline. Anything more than about 5 microns and I'll probably have to restart. So I guess wish me luck. So the first thing I'll do is I'll drill all the way through the part, and doing this will serve 3 different purposes. The first is going to be so I can get the boring bar in and start to machine out that recess. I'll then enlarge the hole to 11mm, but I won't want to go any larger. I'll come in with a boring bar and start to make the recess. Now, as I got closer towards the end, you can probably tell that the lathe wasn't too happy with this whole setup, which probably isn't too surprising given the size of the work, the fact that it's not really being held on by a whole lot of the jaws, and also the fact that this is not a big lathe. So to get around this, I had to swap out my normal inserts for these sharp inserts. Now they're really only meant for turning aluminium, although they do seem to work well in steel, although they just don't seem to last very long. Now according to the calipers, we're maybe 30 microns or so undersized, and if you know anything about precision measuring, you'll probably know that these are not the tool for doing this type of job. This type of job being, plus or minus 5 microns. Now I think the proper way to do this would be to measure it using bore gauges and micrometers, both of which I don't have in this size. Now thankfully I did have a backup method, although I do want to point out that this was me just sort of making it up as I went along, although I'm pretty sure I'm not the first person to have used this method. So what I did was I pulled the chuck off and did a quick test fit just to make sure that it wasn't oversized. Thankfully it's not oversized yet, but I can tell it's very, very close. So what I'll then do is I'll pop the chuck back on, but instead of screwing it back on, I'll simply use the center to hold it in place whilst I sand the recess and make it larger. Doing it this way means I can very slowly increase the size and I can very quickly pull it off and do a test fit. Doing this takes maybe a few seconds versus a few minutes if I screwed the chuck all the way back on. In total, this took about 20 minutes, but in the end, I think the results speak for themselves. That is about as good of a fit as I could ask for. That is just being held there by the fit itself. There's no bolts and there's no wiggle room at all between the chuck and the flange. What I need to do now is get it in the milling machine and drill 3 holes so I can hold it directly in the lathe. Unfortunately though, it's about 20mm too wide for it to fit directly in my vise. I was thinking of bolting it directly to the table using a stud, through the center bore, and using a nut and a clamp to hold it down, but I'm going to be using the center bore to locate the part, so instead I broke out my 2-piece vise. Now the aluminium soft jaw on the fixed end will need to be swapped out for a V-jaw. That will then get bolted down. I'll now set up the moving jaw. Now for anyone who hasn't seen how this works, there's essentially a ball with a thread drilled all the way through it at the bottom of that center hole. Now the top piece, which acts as the moving jaw, will get placed on top of the bottom half, and there's going to be a half sphere with a screw, and that's going to screw into the bottom ball. Now as I tighten the ball, it will pull the top moving jaw forward just a few millimeters, and that will hold the part in place. And it does a fantastic job at holding everything in place. It's a really useful type of vise, and I'm really glad I have it when I need it. I'll then use the drill bit to locate the center of the part, and then I'll set that on the DRO. I now need to drill 3 equally spaced holes to match the hole pattern for the bolts. And to do this, I'll use the hole pattern setting on the DRO. So what I'll do is I'll select hole mode, and then I'll select the center, which is going to be 0, 0, where we're at currently. I'll then select the diameter, which in this case is 108mm, and then I'll enter that we need 3 holes. We now have our XY coordinates for our 3 holes. So all I have to do now is move the table till it reads 0, 0, and that's going to be our position for our first hole. With the holes now drilled, I can now tap them for M8. Alright, and I think that turned out looking pretty good. I'll get it attached to the lathe and we can start to turn it down. I've now gotten it bolted onto the spindle, and the first thing I'll do is clean up the outside. Now machining this is going to be a little bit tricky because I only have 1 horsepower powering this lathe. It's a large piece of steel and it's 1045, so it's going to take a bit more power to machine it than your regular low carbon steel. So I'm going to run this at about 300 RPM, and that should increase the torque by about 4 times. And that turned out looking pretty good. Next I'll turn down the main part of the collet chuck. Now again, the mere 1 horsepower of the machine was starting to show its weakness, So I switched over to the sharper DC GT cutter that I used earlier. And that seemed to work quite well, but unfortunately, as I mentioned earlier, they don't last very long. And since these inserts are actually quite expensive, and I only had a few of these on hand, I opted to find a better solution. So instead, I sharpened a piece of high-speed steel, and then I dropped the RPM to about 140. That should give me about 10 times the torque of the motor. It's not going to be fast, but I should be able to take some really deep depths of cut. And thankfully it seemed to be working quite well. You know, it's not fast, but I was easily doing 4mm depth of cut per pass. And once it got below about 100mm in diameter, I swapped back to the carbide cutters. The cutting performance was about the same, but the inbuilt chip breakers made a much nicer and smaller chip. They're not quite A-bomb 79 chips, but I was still doing a 4mm depth of cut per pass, which for a small lathe like this, I think is pretty impressive. It's definitely the furthest that I've ever pushed this lathe, and I'm very impressed. And once it was about a millimeter or so oversized, I came in with the finishing insert and then took it to its final size. Alright, and I think that looks pretty good. Now I have left a fair amount of steel at the back of the part, and that's mostly to give the chuck a bit of extra mass. Having a heavier chuck really does make a difference when you're doing heavy cuts. It just has a bit more momentum and it's able to power through some heavier cuts. I now need to cut the threads for the collet nut, which seem to be an M40 by 1.5 thread. So I'll get the thread cutter installed and cut the thread. Just double checking that I set the pitch correctly. Alright, and the collet nut is going on pretty easily. Alright, the final thing left to do is take the bore to its final size and then add the taper for the collet. So the first thing I'll do is I'll open it up with a Deming bit and take it to about 20mm. I'll then clean up the hole with a boring bar. Finally, we now need to add the taper, and this needs to be spot on 8 degrees for the collet to compress evenly. So I think the easiest way to set up the compound is going to be to use dial indicators and trig. I'll move the cross slide to roughly 8 degrees and then set up an indicator on the chuck. I'll move the compound 1mm, and according to the calculator, the indicator should move in about 0.139mm. And I'll adjust that until I get that, or just under 0.14mm. Now the first pass was okay, but the surface finish wasn't too great. So I'll swap out the inserts to the finishing type, and thankfully the surface finish did improve. Alright, should be good to go. I've got a piece of precision ground silver steel that's been loaded into the collet. And according to the test indicator, the collet chuck is showing just under 10 microns of run out. And that is pretty much what I was aiming for. You know, I think this is a really good result for some no-name import collets. Just as a bit of a reference, the 3-jaw chuck from before, you know, depending on the size of the part, will do anything from about 40 to 60 microns of run out. So this is heaps better. The final thing left to do is to get 2 holes drilled in each side, and that's going to be for a set of Tommy bars. And they're there so I can hold the collet chuck whilst I tighten the nut. But I currently have work set up in the milling machine and I don't want to take apart the fixture, so I'll get around to doing that in a few days. Honestly, you're not really missing out on much, it's effectively just 2 holes that are drilled on each side. As for the collet chuck, I am so happy with how it turned out. You can expect to see this pop up in a project quite soon, and you'll probably see this quite a lot afterwards. Because I really like collet chucks. They're low run out, they're easy to set up, and they have good grip on parts. And that's about it for now. I hope you enjoyed this video, thank you very much for watching, and I'll see you next week.